Ja, das Quantenjahr 2025 umfasst ein ganzes
encompasses a whole year that is devoted to quantum mechanics. We celebrate its successes and also the future prospects, because it's just exactly 100 years ago, 1925, that the fundamental laws of quantum mechanics were formulated. In Germany, DPG develops and coordinates a large number of initiatives and events in order to make this topic accessible to a broad public, access to this very complex cross-sectional topic of modern research. Well, the offerings are directed towards all people who are interested in quantum phenomena. This includes students, of course, and scientists, people interested in art and culture, and all those who are interested in physics. The Quantum Year 2025 and the celebration is fantastic. It's a fantastic opportunity for me to communicate it to the general public. What fascinates me is the unknown. Maybe you can also compare it. You cannot really understand it from everyday life. And so it's always a challenge to understand what is possible and what can work. Quantum physics is enormously relevant for everyone of us and for society in medicine. It is, for example, MRT. It is the entire semiconductor physics. It is mobile phones. And last but not least, very importantly, also for the energy transition, because PV cells wouldn't work without an understanding of quantum physics. We can be more sustainable and more energy efficient. And this means that quantum technologies will massively retain their relevance in future and even increases. The quantum year is to communicate quantum science as the basis for this and future developments to the general public and to anchor this in the general awareness with a global approach.
Ja, sehr geehrter Herr Vizepräsident.
Dear Vice President Schneider, dear State Secretary Marx, dear colleagues Ketterle, dear participants in the panel discussion that will come later, dear presidents of the American Physical Society, of the European Physical Society and the National Physical Societies in Europe. Well, dear students, many young faces here in this lecture hall, dear university students, dear colleagues, dear guests, and listeners here in this hall and in the live stream. I would like to welcome you to the opening of the Quantum Year 2025 in Germany. Here in the historic lecture theater, which is really absolutely full here at Humboldt University of Berlin, on the initiative of a group of countries with the support of the German Physical Society, the American Physical Society, the British Institute of Physics, and their international sister societies. The United Nations has proclaimed the year 2025 the International Year of Quantum Science and Technology. And the international launch will take place in 3 weeks in Paris. So what are we celebrating? 100 years ago, on the 29th of July 1925, it was Werner Heisenberg who submitted his manuscript über quantentheoretische Umdeutung kinematischer und mechanischer Regeln on the quantum theoretical reinterpretation of kinematic and mechanical relations for publication in the Zeitschrift for Physik. In doing so, Heisenberg, by the way, incidentally in close dialogue with Wolfgang Pauli, found the crucial approach for a completely new fundamental quantum theory at that time. And a few months later, two further papers followed, one by Max Born, which you see here in the lower right corner, Pascal Jordan in the middle, and the other three authors together. And these papers, the two papers on top and in the middle, they are from the joint authors. They already used the term quantum mechanics in the title. In these three papers from Göttingen, fundamental laws of quantum mechanics were in fact formulated for the first time. And these publications, with a bang, so to say, marked the beginning of a new era that was to change our entire world. So what started in Göttingen in 1925 was quickly taken up in Europe and internationally. Physicists such as Erwin Schrödinger, Wolfgang Pauli, Paul Dirac, and Niels Bohr, and many others, immediately made further trailblazing contribution to quantum mechanics. Here in the background, you can see examples of physicists who, in the few years after 1925, advanced the development of quantum mechanics and its applications at breathtaking pace. Within a very short time, a broad body of theory emerged that is still fully valid today. And remarkably, a lot was already determined and still correct today. And remarkably, many young physicists under the age of 25 have contributed to this. So Heisenberg was 23 when he developed the quantum mechanics. And there are many young faces here. So you can become famous within a very few years and in young years. And I'm also very pleased that we have representatives from 16 physical societies with us from Europe and the US, and especially from those countries where quantum mechanics was developed and who made a major contribution to that. In the period before 1925, the number of physical puzzles that could not be explained with the help of existing classical physics had grown. And even the so-called old atomic theory by Bohr and Sommerfeld, you all know them, was still based on classical mechanics, and it did not go beyond phenomenological rules, and it failed to explain various experimental findings before 1925. Now classical mechanics described the macroscopic visible world around us. So, from the movement of planets to the grain of sand in a sand avalanche, all this is in fact classical physics. Although it corresponds to our experience and is easier to understand, it still fails in the microcosm. So, those instruments simply failed. Quantum physics fills this gap on the smallest length scales. It describes the behavior and interaction of molecules, of atoms, and even smaller particles that make them up. And because this happens in the microcosm, it is not understandable or sensible to us, and therefore quantum mechanics seem to be counterintuitive. So the formulation of quantum mechanics 100 years ago made this world accessible to us in the smallest detail, and thus laid a lasting foundation for our physical understanding of nature as a whole. The extension of classical mechanics, as I just mentioned, to quantum mechanics was certainly not a quantum leap. It is used very often by politicians if they want to describe something big, but physicists note that a quantum leap is something very, very small, and I would rather say it was a big leap in knowledge. So the way how new ground was broken by scientists was simply revolutionary at that time. To me, it is an interesting question whether artificial intelligence or a future, maybe super intelligence, fed with all the knowledge up to 1924, would be capable of such a leap in knowledge, because it needs imagination for this, and you have to guess, and you need analogies. And we can discuss this later. Is AI suitable to do something what Heisenberg did back in those days? So what began as a theory in 1925 is now an integral part of our everyday lives. Quantum mechanics has long been the practical basis of the entire information technology that dominates our economy, basically. And as we have already seen in the introduction, various technologies in our daily lives and of our everyday life are based directly on quantum physics. Some from atomic clocks to via photovoltaics as a central renewable energy source to MRI as an important instrument for medical imaging. And with this, we are only at the beginning, because significantly, exactly 100 years after the formulation, after 1925, after the formulation of quantum mechanics, quantum science and current developments in quantum technologies have gained enormous momentum in recent years. And we all in research feel this, that something is developing very rapidly. So what is often called quantum technology 2.0, these new possible technologies cover potential new applications from secure transmission of data through quantum communication to quantum sensors, right through to quantum computing, which is already the word of the day. Such future quantum technologies will, in all likelihood, fundamentally change our world once again. We just don't know how quickly and also in what form. Because quantum mechanics still poses many mysteries today, and the development over the next 20, 30, 50 years is hard to predict. We see it also in classical computer development. And just remember computers from the 1950s to the mobile phone. These are developments that were certainly not predictable. And what will quantum technology bring to us in the future? And this will be the subject of the panel discussion later on. So DPG is leading the International Year of Quantum Science and Technology 2025 in Germany. We are celebrating, as I said, its successes and also future prospects. Under the motto Quantum 2025, 100 years are just the beginning, a wide variety of public events and activities will take place, divided into 5 thematic areas, which you see here, from quantum, these thematic strands from quantum technologies to quantum at school, in music, philosophy, art, literature, and cinema, right through to quantum in the professional world and in society. And the last point refers to the historical perspective, which I already mentioned, but also the look, once again, into the future. So these are, so to speak, the thematic strands. And then there are many events. Let me just mention the highlights, which we can expect. And today it's the opening of the Quantum Year 2025 on the 14th of January. The 14th of January, by the way, is the 180th birthday of Deutsche Physikalische Gesellschaft and the German Physical Society, and we are proud to be the oldest national physical society of the world that was established here in Berlin. And in addition to this, there will be the big conferences of the DPG with 10,000s of participants. So these are the spring meeting in March, but specifically the International DPG Autumn Conference will be held in addition to this. And where should it take place? Of course, at the birthplace of quantum mechanics in Göttingen in September of this year with a top-class program. You can also Google it, including 4 Nobel Prize laureates who will be available there and who will deliver speeches. So let me mention another 2 highlights. One is the celebration of the World Quantum Day in Berlin on the 14th of April, including with the finale of the so-called Quantour. And you should know it starts in Berlin, where this Quantour means that a quantum light source which emits single quantum photons. And this light source, which you see here, has been traveling from lab to lab across Europe and I think also in Turkey. And it will visit 13 top labs for quantum research. And I hope on the 14th of April it will return to Berlin and it will be framed by workshops for school children and a science slam at the Urania. I heard that just yesterday it was launched. So if you are quick and scan this QR code, you can go right to the homepage and register for this event in Urania in Berlin. So, and if you're not that fast, you will find all this on a quantum platform that I will introduce later. And the third big event will be Münster Quantum 100. In Münster, there will be a whole day fantastic closing event of the quantum year in Germany, where all the facets of quantum physics will be represented again, from scientific lectures to experimental workshops for students, a exhibition on quantum technologies, right through to a real highlight in the evening, an audio-visual experience, a symbiosis of music and quantum physics in the evening, in front of an audience of 3,000 events in the City Hall, and we look very much forward to that. So taking part is what matters. So if you have an event in the field of quantum physics that you would like to publicize, then here you can see it again, then register on the platform www.quantum2025.de, and you can upload this, or conversely, and this is also the idea of this nationwide platform, you can use this platform to find interesting events right on site, maybe here in Berlin, and also throughout Germany. And here on the map you see again the places where large central events of the quantum year will take place. And let me also mention, there will also be another activity which is currently being finalized. There will be 100 places of quantum physics in Germany, places of history of quantum physics or of contemporary or current quantum physics. And I think institutions can also apply for this. And this will then be shown on another map. Well, I believe there is no doubt that quantum theory is one of the great fundamental insights of mankind into the world in which we are living. It impacts all of our lives in many ways, with all the opportunities which I just mentioned, and also with risks, definitely. From my perspective, quantum mechanics is a prime example of the enormous social impact that an abstract physical theory can have. Well, and with this, I wish us all an exciting and enlightening opening event this afternoon and a wonderful quantum year in Germany, here in Germany, in Europe and worldwide. Thank you very much indeed.
So, and now I'd like to go ahead according to schedule. The host of this afternoon, the Vice President for Research at the Humboldt University in Berlin, Professor Christoph Schneider, I'd like to kindly ask you to come up on stage and give us your welcoming speech. That's a great scenario to see such a vast auditorium, Marx, filled to the brim with people. It's exciting to see that, and it shows to which extent quantum physics really is amazing. Dear Professor Richter, dear Professor Ketterle, dear State Secretary Dr. Marx, dear international guests of the European Physical Societies and American Physical Society, dear guests, dear listeners in the live stream, dear students of Berlin universities, and of course all other universities in Germany, dear students from the schools. So 180 years German physical societies, that's quite a celebration today. So that is, of course, worthwhile to be mentioned. To me, it's a great honor to be here today and on behalf of the Presidential Board of the Humboldt University, and to be here and to open this new Quantum Year 2025 together with you here in Germany. 100 years ago, in 1925, that is, the formulation of quantum mechanics laid a lasting foundation for our physical understanding of nature. With their great works, as we've already heard, on quantum mechanics, these science turned classical physics on its head and opened the door to a new world of possibilities. Heisenberg's uncertainty principle, Schrödinger's wave equation, and Dirac's equation were just some of the groundbreaking discoveries that put our understanding of physics and nature on a completely new level. In a highly complex field such as quantum research, it is all about collaborating, and it's about exchanging these ideas, which is key to success. In recent years, major institutes, other initiatives and collaborations have been formed in Germany to conduct research into quantum technologies. I think that this is the operandi that we also apply in physics. So here, in a neighboring field, we have seen quite some developments. Over the last decades in Germany, large institutions and centers of excellencies have formed in Germany to conduct research, including the Center for Integrated Quantum Science and Technology in Stuttgart and Ulm, the Quantum Valley Lower Saxony, the Center for Optical Quantum Technologies in Hamburg, the Research Center Jülich, and the Munich Quantum Valley, and all the others that I didn't mention. Please don't be upset about this. Berlin also has a strong quantum community with its concentration of universities. And in the Berlin University Alliance, there's a consortium of scientists that has been researching the potential of quantum digital transformation in an Einstein research unit since 2021. In September 2023, the Berlin Quantum Initiative, funded by the state of Berlin, began its work to develop Berlin into an internationally visible center for quantum technology, to strengthen collaborations and to attract the very talented young generation. Researchers from the Berlin University Alliance with Freie University, Humboldt University and Technische Universität, as well as the Fraunhofer Institute for Open Communication Systems and the Fraunhofer Institute for Telecommunications, have jointly developed the concept Leap Berlin, which was the first co-working space for innovators in the field of quantum technologies, will also open its doors and opened its doors in Berlin-Adlersdorf in 2023. Together with Berlin Quantum, Leap offers wonderful conditions for building bridges from innovations in basic research to industry and value creation. those of us who had the delight to learn something about quantum physics, and this is something that I did when I studied in Freiburg for the state examination to become a teacher, know that this quantum mechanics is more complex than we often realize, and that there is much to be discovered behind all of these mathematical equations, etc. The quantum year 2025, therefore, is the opportunity to celebrate the achievements of the last 100 years and to look on into a very fruitful scientific future. It is an invitation to engage and think about the fascinating concepts of quantum mechanics. Now let's explore these opportunities and challenges of the quantum world. Let's do that together, and let's actively make a contribution towards shaping our future. We are looking forward to a very exciting quantum year 2025. I'd like to thank all of you for showing up on the occasion of this opening ceremony. Thank you for being here. And now let's get started with quantum year 2025. Thank you.
Ja, wir kommen nun zu einem Höhepunkt des heutigen Nachmittags.
We now come to a highlight of this afternoon, the lecture by Professor Wolfgang Ketterle from the MIT in Cambridge in the US. Let me briefly summarize his scientific career. Mr. Ketterle studied physics at Munich Technical University, and at LMU Munich he obtained his doctorate, just like Werner Heisenberg before him. This was followed by stays, postdoctoral stays in Munich, Heidelberg, and finally at MIT in the US, where he became an assistant professor, and then in 1997 became professor of physics, and I think for almost 20 years he has been director of the Center of Ultra-Cold Physics Atoms. Maybe among the personalities in the photos passing through earlier, you may have seen Mr. Bose from India. In 1924 and 1925, Mr. Bose, together with Einstein, made a very important prediction, the so-called Bose-Einstein condensation, named after them. And exactly 70 years later, in 1995, Wolfgang Ketterle succeeded in providing the first experimental proof by creating a so-called Bose-Einstein condensate, so a new type of state of ultra-cold matter. And for this trailblazing discoveries and this big new research field that was opened in this way, Mr. Ketterle then received in 2001 the Nobel Prize. And you can imagine, Mr. Ketterle received many other honors and awards, which I cannot enumerate all of them. This would take too much time, but let me mention just two. In 1997, he was awarded the Gustav Hertz Prize of Deutsche German Physical Society for young scientists. So DPG understood very early on how important his achievements were. And since 2015, he has been honorary member of the German Physical Society. Mr. Ketterle, we are very much looking forward to your presentation, The World of Quanta, from Basic Research to Quantum Technologies. So let us welcome Mr. Ketterle together. Well, good afternoon. Good afternoon. Have a nice afternoon. I'm excited to be here with you in the opening event. First of all, it's about quantum physics, a marvelous, exciting piece of physics which has been fascinating me since I was a university student. And it's also nice to be here in Germany and to celebrate this together with DPG. Quantum mechanics is very different from classical mechanics, and we know there is the quantum wave duality, there is a superposition state, and there is Heisenberg's uncertainty relation. All these are concepts we do not know from classical physics. But there are even more mysterious things, and one is the quantum measuring process. The quantum mechanics is probabilistics, and since quantum mechanics, physics is no longer deterministic, and then we have the quantum mechanical entanglement. Some people call it a mysterious entanglement that you cannot explain by classical physics. All these are differences from classical physics, but they are well understood and they have precise mathematical formulations underlying. I do not have any mysteries in quantum mechanics. The mysteries are in the philosophical interpretation, but not in science. Quantum mechanics is based on firm feet. It can be calculated, and the predictions of quantum mechanics have been tested to many positions after the decimal point. But if the nature is quantum mechanical, why don't we see quantum mechanics in everyday life? And this is due to the fact that due to decoherence, the macroscopic systems, and that quantum effects disappear very quickly so that they cannot be observed. And in this sense, in order to speak with Schrödinger's cat, there will never be a cat which is in a superposition state of dead or alive. So the decoherence will immediately destroy the superposition state, and the world record for the largest Schrödinger cat states is 16 microgram, separated by 10 by less than a centimeter. This is the largest quantum mechanical state where a kitten, or almost a mesoscopic system, which is the largest superposition state that can be observed. And as soon as it is larger, or as soon as the distance between the two states is larger, the decoherence will be so fast that for practical reasons it will be impossible to generate these states. Quantum mechanics describes by its nature the microscopic world, the atoms, the nuclei, the protons, the neutrons, the quarks. And in this regard, but there's also another aspect of quantum mechanics where quantum mechanics becomes macroscopically visible, and this requires low temperatures. Here you see the particle wave duality that you see here, and one equation shows you that the de Broglie wavelength is the wavelength of a particle. It is the longer, the smaller the speed. So this means this wave character of atoms and this delocalization of atoms that have a wavelength, you can call it material wave, you can call them de Broglie waves. It is the wave function, and Heisenberg's uncertainty principle. These are the same perspectives of the principle that a particle is delocalized due to the wave structure, and the delocalization is the bigger, the slower or colder the particle is. So in this regard, there are two areas of quantum physics. Quantum physics rules in the ultra small, where you cannot understand anything with quantum physics, atom structures, atom nucleus structures, but quantum mechanics can also be seen in the large scale if you have very cold temperatures, because as I alluded here for individual atoms, because the de Broglie waves and the delocalization of the particles becomes very large. So, how can you achieve very low temperatures? And there are different methods in different areas of physics, but the method that revolutionizes temperatures is cooling by means of light. You all know light. Light has energy, h cross omega. This is the quantum of energy. But many people, and maybe even some here in this room, maybe do not know the light also transfers momentum. Light can also exert a force, and this is the radiation. Momentum. If I hold a lecture, then I always want people to learn from this. The question is, in Germany, or everyone should know, how much energy do we get from the sun? So if you have a solar panel that is 1 square meter large, can you operate a computer or a coffee machine, or how much energy do you win from this? And I think most of you who doesn't know. Thank you for being so frank. So the solar contents. Sorry, I was too fast. So just remember this idea. What I'm going to show you here before I'm going to talk about the solar constant and the solar cells. The light force was observed earlier. Already in 1619, Johannes Kepler saw that if you look at comets, the tail of a comet always points away from the sun. By the way, we have two tails, one plasma and one dust tail. The plasma tail, these are charged particles, and the dust tail is deflected due to the light pressure force. It always is directed away from the sun. So this force has been known for long, and now I would like to tell you what this light pressure force is and what you should take home. In one area, the force can be very small, and in other areas, it can be very large. So the solar constant is around 1 kilowatt per square meter. So with a solar panel of 1 square meter, you can operate a coffee machine. So, but then we have the light pressure force. Who of you knows how large the light pressure force on a solar panel is? Should you know this? 1 square meter solar panel. How large is the light force and the radiation pressure of light? It's very simple. You simply have to divide by the light speed. And if you divide the energy by the light speed, then you obtain the impulse, and this means if you have the energy per square meter and if you divide it by the light speed, then you have the radiation pressure, and the pressure on 1 square meter of solar panel is 4 microAn per square meter, and this is the weight of a very small sand grain. So at the end of my lecture, if you do not remember anything, but please remember a solar panel of 1 square meter receives the light pressure from the sun, and this force corresponds to the weight of a small grain of sand. If you remember this, then you learn something.
Now, with a solar panel, this can be neglected. So the weight of the solar panel, wind pressure, etc., all of that is playing a much larger role here. So here, but it does come in as a very important effect when I look at light, at how it is affecting microscopic small items. So a small force may have a large impact here. The light force may cause atoms 10 to the power of 5 to 10 G. That's how it can accelerate or decelerate these atoms. And so therefore we can get very cold atoms. Laser beams from all directions exert force by light on these atoms, and then these atoms can be cooled down from room temperature to the 10th or hundreds of microkelvins. And then we have super cold atoms, and with those super cold atoms we can do very exciting physical tests. This is what our laboratory looks like. You do have some vacuum machines, there's some optics, and there are some spools, but all of this is a tabletop experiment, and it's a relatively small group of PhD students and maybe one postdoc can make new discoveries in quantum physics using this. Here you can see cold atoms with your bare naked eye. You look into this vacuum chamber, and this yellow arrow shows you a small yellow sphere with a few millimeters in diameter. This is not. This is sodium vapor. It is 100,000 times colder. And this was cooled down by the force of laser. And here you see something similar in a slightly different color. The atom that was cooled down to microkelvin here is a dysprosium atom. This is a lanthanide, and with that you have very exciting quantum mechanical research, because this material is the strongest magnetic material in the entire table of elements. So let's take a closer look at these atoms. How is it we may discover quantum phenomena using this? Now, I've shown you the vacuum chamber in the laboratory. Now, what this is all about is this here. You have a few thousands or maybe up to 1 million ultra-cold atoms sitting right there in the middle of this vacuum chamber. And the vacuum chamber is the world's best refrigerator, because then here we can isolate these atoms from their surroundings. What is it that we can monitor here? One thing that we may see is that you switch off the magnetic or electrical fields that keep the atoms together, and then they extend again, and then the atoms are shown to a digital camera, and then some light is shed on them, and then we monitor these. What is it that we achieve by it? Now, when we look at the shadow image of these atoms, there's a certain point in time where we switched everything off, and then the atoms go out again, and then you look at the shadow image, and the diameter of this cloud gives you directly the velocity. And you have the radius, and then you divide it by the travel time, and the kinetic energy equals this. So therefore, we can directly determine the temperature. So therefore, we can directly calculate microkelvins, and we can directly observe them and measure temperature without having some device sitting in there. So this laser cooling method was developed in the 1980s, 1990s. It was discovered and further developed, and this is my specialist field. In the early 90s, I started to look at this and research this topic, and one of the main reasons as to why we wanted to have cold atoms was the following, and now we will talk about quantum technology. One of the reasons was that we wanted to have more precise atomic watches. This standard before we had cold atoms was shown here on the left-hand side. This is a conventional atom beam clock, and there's a cesium beam, and here you have a cyclical movement in the cesium atom, and that's the cesium clock. With frequency and time, this was the standard. But it also means that cesium with 100 meters per second, with a thermal velocity, we have it moving. And then, for example, in a very long machine, you had only a few milliseconds to read the actual time. As soon as you could laser cool atoms, you could slow them down 1,000 times, and then you were able to read the time 1,000 times more precise, and therefore factor 1,000 is how much we improved this atomic clocks. This was the motivation, and in the result we have very precise atomic clocks and a lot of new findings in quantum mechanics. This one physics is gravitation red shift. All of you know, if you have a twin sister or twin brother, and if that twin brother or sister was to scale a mountain, then your brother or your sister would age faster because of the offset in gravitation. All the clocks would tick faster, both atomic clocks and biological clocks tick slightly faster when you are on top of a mountain. You should think about how much you fly, because in an airplane you age faster. Now, this gravitational redshift for 1 centimeter, it is 10 to the power of minus 18. But this gravitational redshift can now be measured more precisely with atomic clocks. And then some basic research that was done in order to measure gravitational redshifts. And now there's suddenly a new application for this, namely to measure heights in different locations. So here, for example, PTB in German city of Brunswick and Max Planck Institute in Munich. Here we can measure this directly by comparing 2 atomic clock frequencies and then compare that. But atomic clocks are much more precise. With the most modern atomic optical clocks, we can measure the gravitational redshift on a 1 millimeter scale. So if you have 2 of such clocks and one is standing slightly higher, this clock is shifting, is ticking slightly different. And so therefore now you have with this atomic clocks an instrument with which you can look at gravitational anomalies and measure other things. So because something that was done in basic research now suddenly has an impact on some true applications. It's not something of the future to see exactly where tectonic plates are shifting. Something like that could be seen in the future. And it may be an early detection device for earthquakes. Nobody thought about it when we did the basic research, but this is where we're at right now. What is important in quantum physics is the observation of single atoms. Now, let me dive deeper in this exciting topic. The observation of single atoms and single photons. Let me talk about that. We heard about Erwin Schrödinger and Werner Heisenberger before. Mr. Richter has talked about this with his historical overview. And these are a few quotes by Schrödinger and Heisenberg. Schrödinger said, "We are not experimenting with single particles." He said, to experiment with individual particles would be comparable to having dinosaurs in a zoo. Werner Heisenberg said the atoms or elementary particles themselves are not real. They are only a potentiality, but not a matter of fact. Well, here, and this is exhibited in the German Museum in Munich, you see an iron trap by Mr. Toschek in Munich and Heidelberg, and he was one of the first to have seen single atoms. What you see right there, where the yellow arrow is pointing at, here, this very small dot in the middle, this is not dirt, but this is a single barium ion that we can see in this light. And a few decades ago, when I was in Hamburg with Mr. Toschek, I was able to see through a microscope, and I, with my own eyes, saw the light of a single atom. So, despite the fact that Schrödinger and Heisenberg were skeptical, some experiments can be done on individual single atoms. This is an image from one of my laboratories here. Individual rubidium atoms were absorbed here. Here, for example, 100 atoms on the left-hand side, and on the right-hand side, it's slightly blown up, and therefore you can see precisely in which position these atoms are and then identify quantum phenomena. What is very important and plays a large role in quantum physics is the concept of quantum jumps. There's this concept in quantum physics that parts have a certain energy level, but then suddenly, abruptly, they jump from one to another, for example, by emitting a photon. And this is something that, as a matter of fact, shall be happening abruptly. And the question is whether or not there are these quantum jumps and whether or not we may observe these quantum jumps. This question was a long discussion amongst physicists, and sometimes some people think that quantum jumps are also happening in our brains, but because of decoherence, I do have major doubts about it. But back on the topic of quantum jumps, let's go back to Bohr and Schrödinger's discussion in 1926. Schrödinger, the whole idea of quantum jumps necessarily leads to nonsense, is what he said, nonsense. And Schrödinger said in different words, if we are still going to have to put up with these damn quantum jumps, I'm sorry that I ever had anything to do with quantum theory. And this is what he is saying here. And even in 1952, 20 years had passed, and Schrödinger had said that quantum jumps to him are like the epicycles of the planetaries and the theory of epicycles. So that's how you describe a solar system, because before they found the Copernicus system. So to him, this was an erroneous pathway of quantum physics. Here we see quantum jumps. You see that in the same ion trap that I've shown to you here on the left-hand picture. You see this fluorescing light from a single atom. It goes on and off, on and off. And this is precisely because one single atom is between two different energy levels, jumping back and forth between those two levels. Can that be done with photons too? Can that be observed in individual photons? Yes, but it's much more difficult because usually you have a photoelectric effect, and that's what you use to observe photons. There's a click and then the photon is destroyed. So it's more complicated. But the Nobel Prize was awarded for this, and in individual photons, quantum jumps could be proven. And in order to do that, you had to observe photons, and that's very difficult to do because it moves away with light speed. So Licht und Materie is another exhibition here in the Deutsches Museum, and modern quantum physics shown in a museum. Between these mirrors, a microwave photon is reflected back and forth, and a single photon, let's just imagine this for a second, for 100 milliseconds you may observe it. In 100 milliseconds, this photon is moving with the speed of light, 40,000 kilometers, so once around the globe. And in the laboratory, when you want to keep it right there, more than 1 trillion times, it must be bounced back and forth between the mirrors. And to do that, you do need mirrors with a reduction coefficient at 100% minus 1 billionth. And these are these supraconducting mirrors that are shown in said museum. And here, when you have this photon and store it for 100 milliseconds, then you can send atoms through this resonator, and the atom is feeling the electric field and therefore you have an offset of energy, and that can be measured. So you can measure 100 times, and here it's shown that the same photon is still present. So to me, this is exciting because in the history of quantum mechanics, this is really a great leap forward. Here you see blue and red. You see this on the basis of the interaction with the field, it changes. So what you've observed here is you didn't have a photon for half a second, and then there is a photon for half a second, and the same photon is detected for 100 times, and then it's gone again. So experiments on single photons. Schrödinger would not have thought this possible. But of course, it's a great accomplishment of quantum science that we were able to do experiments on individual photons, on individual atoms, and also to look at these atoms in one single quantum state. So to have this very pure and to control it in accordance with everything that we know about quantum mechanics is made possible by quantum mechanics. So once we've achieved that, the question is what can be done after that. If we quite successfully looked at individual atoms, photons, etc., what is it that you can do after that with 0 atoms and 0 photons? This is only going to be the vacuum. But of course, something you could do after that is if you control the building blocks, then you go through the reduction to other complexities. You may not only look at individual atoms in a quantum state, but many atoms in a quantum state, and define this quantum state and look at it. So with photons, this is done in the laser, and with atoms, this is done in the Bose-Einstein condensate, as I will probably show you. But then there's also this other possibility. A number of different atoms is used to prepare certain quantum statuses, and then this is leading us up to this.
Single particle quantum mechanics is something most of you will know, the wave-particle duality. And often you learn at university, at least in the beginning, you learn single particle mechanics because it's still simple. As soon as you have two or more particles, you have entanglement and you have correlations which are extremely difficult to describe, but for research and for quanta phenomena, they offer a lot to understand. However, it is also possible to have many atoms in order to have macroscopic quantum phenomena, and this means that many atoms have precisely the same quantum state, and then the wave function becomes a macroscopic material wave. And so atoms form a macroscopic material wave in the same way as the laser has the macroscopic field of many photons. And this phenomenon of the macroscopic material wave, the Bose-Einstein condensation, and that's the name, this is the basis for superfluidity and superconduction. And this means if you have temperatures that are low enough that the de Broglie waves become longer, then you have a phase transition where the Bose-Einstein condensate is formed, and the Bose-Einstein condensate can be understood as some kind of macroscopic material wave or many, many particles who march in synchronism. So how to observe the Bose-Einstein condensation? You remember, I said it before, if you observe cold atoms and if you measure low temperatures, and you could do the very same in order to observe a Bose condensate. I showed you earlier, if the atom cloud expands, then you can take a shadow picture. And now imagine that from measurement to measurement, the atoms become colder and colder, and then you will see that the shadow picture shrinks because the thermal movement of the atoms is cooled down. And here you see a shadow of atoms close to the Bose-Einstein condensation, and suddenly there is something in the middle. It's just like a stone in a cherry. You have elliptic Bose-Einstein condensation in a round thermal cloud, and here you literally see with the eye of a camera how atoms suddenly march in synchronism and form a macroscopic material wave. So the Bose-Einstein condensation can be explained with the material or the de Broglie wave picture. If you have a high temperature, you don't need quantum mechanisms because particles move. But basically, and the second panel shows this, but basically atoms already have a delocalization. They already have a wave character, but as soon as the distance between the atoms is much larger than the expansion of the wave, it doesn't play a major role. But if the atomic waves touch and superimpose, then you have synchronism as a result, and the Bose-Einstein condensate is formed. So what plays a role here is the fact that atoms are a wave. And now I would like to connect from the old quantum physics to the present. I would like to show you measurements which are just a few months old, where for the very first time this thermal material waves were observed. And this also shows, in conjunction with the discussion that we have, it is not just about technologies. The exciting thing about quantum physics and the biggest potential is that we still can make discoveries which are sometimes even extremely simple, surprisingly simple. So how can the atomic de Broglie wave be mapped? I showed this earlier. We have the possibility to detect individual atoms, and here we have a gas of atoms. We switch on light and we see every atom as a bright dot. So what we can do now is, maybe I should go back. This picture can be analyzed, and you cannot see it with your naked eye, but you can ask yourselves, is the probability that two atoms are closely to each other, is the probability larger than the atoms are a larger distance away? So we look at the correlation and we ask whether a pair of atoms that is neighboring, so close to each other, is the probability larger for this. And all we do is, now we perform a statistical evaluation. What is the probability to have two atoms with this or that distance? And we divide this and we normalize it with a classical statistics. So, for example, if you are blindfolded and simply throw balls into this board, and sometimes you have close neighbors and sometimes they are further apart. And this is the classical statistics. And what you see here, it's simply mapping of the normalized probabilities to have two atoms close to each other. And here the blue curve shows if the atoms are cold, then there is an enhancement, a higher probability that two atoms are close to each other. And this distance that we measured here, from 1 to 3 micrometers, this is the thermal de Broglie wavelength. So statistics of an atomic picture shows you directly what the thermal de Broglie wavelength is. The Bose-Einstein condensate was a new material. In atomic and molecule physics, we always looked at individual atoms or the collision of two atoms with two atoms, but suddenly we have something in physics that is a new material, and material, an unusual material. It's very cold, it has a waveform, it is supra-liquid, but it is a modern quantum material. And to us, and for the last decades, it broke new ground. We want to use cold atoms in order to do controlled material research. And these ice-cold atoms will be used as Lego blocks. And by means of laser beams, we want to bring them together or to form new materials. And this quantum Lego has been called a quantum simulator, because you can use it in order to simulate material properties which you cannot calculate. To explain this, with a simple example, the Bose-Einstein condensation of atoms simulates the supraconduction, because the atoms that we are studying here have properties like the electrons in a supraconductive material. So we can say the Bose-Einstein condensation was to some extent a quantum simulator for superconduction. Well, fair enough. And I deliberately show you a very complicated formula. What I want to say with this is, if we want to research new materials, then we usually know the equations. We know the equations, how electrons behave in metals that describe atomic structures. It is the Schrödinger and the Dirac equation or extensions of these equations. The problem being that the equations are relatively simple, but we cannot solve them. We can only solve them for a few particles. But in physics and in technology, there's a long tradition that equations are not solved numerically, instead via the properties of special materials. And this brings me to an analog computer. When I was a university student and I had my practical studies, I worked with such a box, which is an analog computer. Who of you still knows this? You can use it to solve differential equations, because an operation amplifier in series simulates or implements, and it implements a differential equation, and you program this computer in this way. And the output and the result of such a calculation is then recorded using a chart recorder, and you can use it to solve differential equations. We did this, and now digital computers are now doing this job. But the vision which Feynman then applied to quantum mechanics was, can we perform analog simulations of quantum mechanical processes? In this sense, we use cold atoms that are easy to control in order to create a new solid body or to research solid bodies and to make predictions. And in this sense, the equations of other materials can be solved using cold atoms. And the reason for this is we will never have the computing power of in digital computers to simulate quantum mechanical systems. This is only possible for small quantum systems. If you have 300 particles that have a spin up and spin down, they have a Hilbert space of 2 by the power of 300, 2 by 300. And this number is so large, like all the protons in the universe.
Wie macht man Quantensimulation?
How can we do quantum, or how do you program an atomic quantum simulator? I already presented the cold atoms, and now we can change the atoms. We can bring them into a new state and a new material by using laser radiation, radio frequency, and microwaves. And with this, we have metals, insulators, superfluids, and other materials that we research. And to give you an example here, if you have the atoms in a periodic structures and the atoms have 2 states, blue and red, a lot can happen here. But for example, it can have anti-ferromagnetic or ferromagnetic odd materials. And these ferromagnetic materials can be simulated using atoms. And what you see here is a work carried out by Markus Greiner in Harvard a couple of years ago. And what we observed here is this chessboard pattern of an anti-ferromagnetic pattern. Here, cold atoms were used here in order to have a simulator for quantum mechanical magnetic materials. Or in my working group, we had a strip pattern that we generated of atoms in the blue and red state. And then we looked at these strip patterns, how they developed. And we simulated the quantum mechanics of a magnet. At a very fundamental level, we understood this. In a quantum magnet, whether it's ballistic or recursive. Right. So what I presented here by the example of magnetic materials and the Bose-Einstein condensate is what you can call an analog quantum computer. We have a quantum system which implements a physical phenomenon or simulates in this sense. But of course, if you want to use quantum mechanics for calculations, you do not want to have only analog simulations. You also want to have a digital quantum computer. And I would like to spend the last minutes of my lecture on this. A quantum computer, it's about qubits. And let me give you the example of 2 socks, or many socks a little bit later. A classical sock has a certain defined color. It's red or it's blue. But a quantum sock, a 2-state system, a spin up and spin down, can have a superposition state. And if you then look at the superposition state and a certain probability, it's either red or blue what you see. So socks like this do not exist in quantum mechanics. They're only red or blue because they have only 1 quantum state. And if we have more socks, in this case we have 10. Then we have 2 to the power of 10 permutations, and this means the Hilbert space is 2 to the power of 10. And if you have 300 socks, I already said this earlier, then we have 2 to the power of 300, and this can be compared to the number of protons in the universe. So a system of 300 quantum particles has more memory capacity as a computer than any digital computer in the world. A digital computer would have to be larger than the universe in order to have the memory space like a quantum mechanical system of just 300 particles. And this shows the potential for quantum computers. But decoherence is, of course, a major challenge here. And now, in order to explain what the potential or the performance of quantum computers is, let me say the following. If we have full control of a quantum system, then we can also determine how the quantum system will develop as a function of time. And the quantum system that stores information, the development of a quantum system is a calculation process. And if we assume the example, here I arranged the socks in a way that you can see a pattern. And the pattern is like a digital picture, and the calculation using this quantum system is like analyzing a picture. But now the point is a quantum memory can be used to create a superposition state of millions of images, and the quantum computer can then simultaneously analyze 1 million pictures. And this is the potential for the bigger performance and the function of quantum computers. And so quantum mechanics is a new resource for calculations. It sounds very good in the abstract world. In the practical world, it's very difficult. And it was shown just recently that quantum computers have a quantum advantage for certain applications, that they can calculate or perform certain tailor-made calculations, that they can perform these calculations faster than a classical computer. But the development is still in its infancies. It will take decades until quantum computers will be able to solve practical tasks, but the developments are breathtaking. And this also led to major activities in research. Mr. Richter already said this. Worldwide, we have initiatives to use quantum effects for technologies. And the technologies we are talking about here is communication, it is computation, it is simulation, and quantum methodology. And I tried at least to give you some examples in order to describe the quantum methodology with the atomic clocks and the quantum simulation, the Bose-Einstein condensation, to research magnetic materials, the technologies. And there are major problems to be solved. But researching quantum physics is extremely exciting, and I think there's one prediction I can make. We have absolutely exciting times for quantum science ahead.
Thank you, Mr. Ketterle, from the bottom of my heart for this exciting presentation in which you talked about the fascinating quantum physics and made it so clear to us. The last slides have shown this to us, namely this smooth transition towards the next point on our festive agenda for this afternoon. And now we will be talking about the future of quantum mechanics and the panel discussion, Quantum Physics, the Next 100 Years. Jacob Beautemps, please come up on stage. Mr. Beautemps just finished his PhD in the didactic of physics, or are you still doing it? No, you're finished. So we congratulate you on your doctorate. Dr. Beautemps will be leading this panel. He's much renowned as a YouTuber, and last year he was awarded the DPG prize for publications in the field of natural sciences 2024. So I think he will introduce us to the panelists. The floor is yours. Thank you. I think all of you hear me just fine. Thank you for this opportunity to be here. It's quite an honor to talk right after a Nobel Prize laureate, and it is a huge honor for me also because I have a great panel with exciting panelists this afternoon. We will be talking about this very topic that we've just heard about, and we would like to dive deeper. We heard quite a lot about different aspects that we now would like to discuss even in greater detail. Now, we will be talking about quantum physics, but more importantly about quantum computers. And this is something you understand when you look at the panelists. Dr. Jan Goetz from IQM Quantum Computers, please come up on stage. Professor Tommaso Calarco of the Research Center Jülich. Dr. Henry Marx, State Secretary for Science and Research. Dr. Sabrina Patsch, scientific journalist. And Dr. Heike Riel of IBM Research Quantum Europe. Great. Looking at us, we can already tell that quite a lot of knowledge is represented here when it comes to quantum computing, but nevertheless, I'd like to take all of us one step back talking about physical aspects, because we've heard about this. Why is quantum physics so important, and why is it important to engage in it? But one other thing that you stumble across when you talk about quantum physics is the fact that it is somewhat complicated. And so therefore, my very first question before we dive deeper into the topic, what's the deal with quantum computers? What's the physics behind it? And why is quantum physics so complicated? Ms. Patsch, you've done quite a lot on this, and quite many contributions were published by you. What is your assessment? Why is it so difficult for us to understand quantum physics? I think that there's a number of different reasons applicable to that, and we've just seen one of those reasons play out here. I think one reason is that quantum objects that we take a closer look at are very, very small indeed. We don't see them in our everyday life. So something like atoms, okay, there are some experiments that can be done, but most of us don't have the equipment right at home. So most of you probably never have seen an atom with our own eyes. But what we can see in everyday life, what we can see is difficult to imagine. In addition, these super small particles do strange things. They have strange superposition, uncertainty. So these particles can be at two places at the same time simultaneously. And this, per definitionem, this is not imaginable. Our brain works classically, but the world we see works differently, and we are not capable to really process this with our brains, what is going on in the quantum level. And in addition, quantum physics has a bad reputation. Richard Feynman said, those who believe they understood quantum physics did not understand it. This quotation is rather famously known, and so therefore quantum physics is very difficult. You cannot understand it. So how is it that I, as a layperson, should be able to understand it? And so therefore many don't know about this, because quantum mechanics is a rather fascinating world, and who wants to understand it is able to understand it if you find some kind of access and engage. So this may be our approach today, to find just the right approach to it so that we engage. So I ask all of you, do all of you agree with Mr. Feynman, or would you say, well, quantum physics that can actually be understood? So, Ms. Riel, the cat is a much worse example. So this understanding of physical processes is not at all something that makes sense in our everyday life. And so here, if you don't experience something yourself, then it's more difficult to understand it. And so therefore, I can only say these small parts, you don't see it other than in a laboratory. But what does it mean to understand and then to get accustomed to it slowly? I think when I studied physics, I was accustomed to it gradually, and then of course you do understand the mathematics at play, and everything makes sense as logically, and then you understand it on the basis of the laws of nature, and then you understand it in quotation marks. So to get accustomed to, and that of course is something that this term helps us to gain this normality, and then over time you gain intuition. And I think intuition is an important aspect here, that many researchers, when they work on this for years and years, they do get this kind of intuition for it. So of course we want to have this intuition, but also this possibility to engage, to dive deeper and then to experience these things and understand them. We would like to do this in practice over the next 30 minutes. One thing that stood out for me is whenever I tackle complex topics, then it's helpful to look at one single aspect that maybe even has a practical application. And this is quite befitting to our panel, because quantum computers would be something that people could look at. And maybe Mr. Calarco, the information just provided to you and all of us, could you explain to us what is a quantum computer? Oh, that is a rather simple task, right? Oh, so what is a quantum computer? A quantum computer is something with individual parts. And with these parts, it's going to do a computation. And as we've already heard by Mr. Ketterle, with the red and blue socks. So here, just imagine you have a problem to solve. You're in the middle of a labyrinth, and you need to find your way out. What is it that you usually do? You say, OK, I go straight to the left, to the right, and I must now choose either do I go left or right. But at some point in time, I will go into a cul-de-sac. I cannot go any further, so I go back. So I said, well, at this point, I turned left. Now I don't go left again, because now I go right. And so one step after the other. In the end of this iterating chain, you get a sequence of left, right, left, right. That's the solution to your problem. But now, if in each intersection, if you were to be able to walk both left and right at the same time, then you would be at the exit straight away in one run. But the problem is that we have to understand how parallelism works. We may have an intuition about it. That's understood. And this is because we work with individual parts and everything that we've heard about before. But there's this very small, peculiar problem. Now, the quantum computer does know which is the correct way out of the labyrinth, and I want to know it too. But unfortunately, I am a classical computer, meaning I have to look at all of the different possibilities. By chance, I take one solution that may be wrong or right. I don't know. I didn't get anything out of it. Now, that's the very reason as to why it opens up so wonderful possibilities to do things at the same time, just as the computer to read it out allows us an algorithm. So we have some kind of procedure at hand. It allows us to do some computation and gives me a result. And this is very difficult here. And there are only a few examples for very special and unpractical problems. We have quantum computers, and this is why we need to think about this in the future to find further algorithms and further solutions. So it started so nice, it sounded so nice when you said that you have all the different solutions at one time, but then suddenly you learn, well, this is not too much benefit because it doesn't yield too much of a result. So this is rather befitting to how we perceive quantum computers, because if you read about it, you say, yes, there's this great supercomputer, which is twice as ironical, if you will, but people say that this is a computer that's much, much faster. But it's a misunderstanding, because the classical supercomputers are something totally different than quantum computers. Ms. Riel, maybe because you are working on this quite a lot, how would you describe the difference between a classical, very fast supercomputer and a quantum computer? How would you describe the difference? HPC, high power calculation, is done by a number of different CPUs and kernels, and you try to do, to some extent, analogous, so data, computation. So a supercomputer, to me, is looking at a rather complex task that I cannot compute at home. That is a very important question, and this supercomputer is able to compute it in a very complex situation with all the technical aspects that I throw at it. But a quantum computer is still in its infancy. We've heard about it, and we are currently working on ramping up the computational powers and then also to integrate them into the supercomputer hardware. And what we want to achieve as a company is that we want to support and assist others in resolving these important computational tasks. To us, it's not important how we do it. To us as physicists, it is interesting how it is done and to find and apply new methodologies and to improve computational powers. But to the customers, this doesn't play any role. To the customer, it's important to resolve the issue with less effort in energy, less effort in financial aspects, and to get the task done. But this is not the difference between quantum computers and classical computers, right? No, I'm sorry, I understood you wrong, because my question was about the following. When you read some articles, you have the feeling that they talk in these articles about classical computers, and then they talk suddenly about quantum computers, and they say that this is something like a standard computer, but slightly faster. No, that's a wrong description, not just slightly faster. A classical computer works with transistors on and off, and we have seen such an image where you switch them on and off, these transistors, and then in quantum computers it's different. But with the old computers we have bits, either power or no power, but with quantum qubits we can have quantum computations. And over the last several decades, the transistors they got smaller and smaller, so that a huge computational power can be generated by doing it. But this is classical 0 and 1s. It's not 0 or 1. So in the digital world, I have bits, 0 or 1. I know whether or not a bit is a 0 or a 1. And as we've heard in quantum mechanics, this works totally different. So to speak, in quantum computers, you have basic conditions and all the conditions in between, and all the solutions are prevalent at the same time. And then you have to find them through the algorithms, looking at interferences, and then you need to find the solution and generate the solution through that. Mr. Calarco, I have something in my pocket that I wanted to show you. Here in my left pocket, there is something that all of you are very familiar with. I think all of us have seen it before. It's an iPhone. This is one device that was a result of the first quantum revolution. So, as we've heard before by Mr. Ketterle, without the ability to manipulate photons, we would not have this mobile communication device. But in my right pocket, I have something that you haven't seen and you don't know that it exists. Samsung Galaxy Quantum is the name of this device, the first consumer electronic device of the second quantum revolution. It looks very familiar as well. It doesn't do quantum calculation, doesn't do quantum communication, but it does do something else that's very interesting, not only when it comes to computers, but here in my pocket I also have something, and this is a chip that's able to do 2.5 square millimeters in size. When I was young, like our presenter, Beautemps, so the entire content of this table, full of lasers and mirrors and other apparatuses and devices, and now all of this was brought down in size to this. And what does it do? Precisely what you talked about before. This creates photons that go at the same time to the left and to the right. And here on this, there's also photon detectors, and they say, well, has this now gone left or right? And then you have a number that's generated by chance. It's not a quantum calculation, but the smallest element is this. And what's going on up there? Well, they want to see the card. Oh, okay. So this is useful because by that I can generate chance numbers, and they're required to ensure safe classical communication. These chance numbers may never be simulated. It may not be predicted what the next number will be, and only with quantum systems you would be able to do just that. So this is the smallest that we currently have available. It's not very powerful, but we can claim that there are many other applications before we have a quantum computer. There's quantum communication, quantum processors, as our president has said before. It's very broad, but it's very specific.
Very nice example. Thank you for demonstrating this. It was also good for me. It's a fantastic example. And in fact, we will also refer to this later because quantum communications is also very relevant, also in conjunction with quantum computing. And all this goes hand in hand. Mr. Goetz, you build quantum computers in your organization. So just a short poll. Who in this room has an idea how a quantum computer is built? So it's a mixed. There are some, I would guess, professors of physics, but also many hands which are not raised. Maybe briefly explain how can we imagine how is a quantum computer set up. In principle, it is a calculator. Imagine a calculator. Maybe you know these black and white pictures with these old real computers where persons standing in front of them. These persons were computers who connected the cables, who plugged the cables, and this is how the machines look today in quantum computing. It's large machines, some square meters footprint, and there is a chip, of course, and a semiconductor that is cooled down to very low temperatures, and then there's a lot of control electronics, and this is how these devices look like today. And of course, there's a lot of potential for miniaturization, and of course also for increasing computing power, but basically I say the machines that we have today already work in principle. You can solve algorithms and you get a sensible answer. Maybe they are not faster than a high-performance computer, but it has a benefit, especially here in universities when it comes to training and education. Let me briefly refer to the beginning of the discussion. Can we understand quantum physics? How do we understand things? Think of gravitation. There's the story of Newton sitting under the tree, and then there's the apple that fell down, and he understood gravitation. And if I go to the street and ask people, why do attract masses each other? So what is the deeper background of this? Then the majority would say, we cannot explain it. And I think we must get away from this in quantum physics too. And we must say we cannot understand it because we cannot observe it. We do not see apples falling down in quantum physics because we cannot observe the individual atoms in our lives. And this is also important in quantum computing. In order to come back to the beginning, we must not shy away from entering into this topic. So students and developers must start calculating, using these devices for calculating. And we must be prepared for the time when the technology has reached maturity. And this is something that we do at our company. We will refer to this later, how these computers are in fact built. Maybe one question to Mr. Marx, but maybe a question to the audience, because we already heard this several times. Who of you shies away from entering into quantum physics, or who of you has the feeling quantum computing, this is too difficult to me, and I have the feeling that after this event I will no longer go into this topic again? There is one show of hands, two people raising their hands. Okay, we must say this is a relatively large error susceptibility, but maybe I would also encourage you and say, don't shy away from quantum physics. But now I come to the real point, Mr. Marx. How must the understanding of topics like quantum physics and quantum physics, how much of understanding do we need in our society? How relevant is it for us as a society and as a democracy to have an understanding of these definitely complex topics? I think it is relevant for two reasons. On the one hand, this is due to the fact that if you look at Germany and Europe over the past 20 years, we overslept a revolution or two. AI, for example, where we are currently beginning to work on it, but we are not really the first movers. Stem cell research, where we, maybe for data protection reasons, we were a little bit concerned. This does not apply that much to quanta. It doesn't sound nasty, that is an advantage, but maybe there is not this fear of going into it. But what it is important, we must be open and we must develop more openness in relation to these topics. And the other point is, of course, we need the people. We are many people here who already did a lot for quantum research or students on quantum physics, but this is also necessary for the next and for future generations. So the understanding or the skills of fundamental sciences, physics, mathematics, and so on. We are mainly talking about physics today. This must be developed further, and this is extremely important in order to ensure progress and innovation in our societies. So it's really interesting and exciting. If you look at research policy, then it's about funding and funding structures. And at the end of the day, it sounds banal, but at the end of the day, it's always people who do it. And you can win them only if it's highly relevant in society. And so I would be happy if that increases. So in the end of the day, it's two aspects. Or would you like to add something? I think this understanding technologies means that you can also become creative. You can also drive innovation on your own, so there are fewer barriers to use these technologies. And the second point, or the other point, which I also consider to be very important, is if you do not know something, then you can also shy away. And we tend to look more at the risks than at the opportunities. And then you tend even more to see the risks. And then you lose more of innovation and progress that you could extract from these technologies, or also of economic benefits that you lose. And you miss things if you still evaluate while others are already implementing. And so this understanding and this communicating of this understanding is very important. And nanotechnology was a similar development. Nanotechnology, 25 or 30 years ago, it was strongly discussed and intensively discussed. And today, this technology is in place. And we must always deal with risks of new technologies. And therefore, it's also important to address and to transparently communicate the risks so that fears are taken away. So fears and both opportunities and risks must be discussed, and risks must also be mitigated at the same time, which is also very important. That's a good point, which I would like to begin with. We're going to talk about the risks a little later, but let me first begin with the opportunities. And maybe Mrs. Patch, if you want to add something. I would like to add something. I think there's one major risk if you do not understand a technology, is that you quickly misunderstand it. If you do not understand quantum technology, then you may believe any reports which are not true what quantum computers can do. And we still do not know what quantum computers can be beneficial. And if you have a basic understanding and if you have the possibility to critically review reports, then it's easier for you to understand it. And because research can no longer do justice to the picture, because if we expect that we will have a quantum computer that can solve everything, which is much faster and greater than anything we have, then you are simply disappointed because research cannot deliver on these promises that are misunderstood. And therefore, it's important to understand what quantum computing can in fact do. The big advantage is it was promised that AI will solve all our problems, so quantum computers are not that much under pressure. But expectation management is an important point, and we'll talk about this later. But in films, it's always called the cliffhanger. And so we are going to talk about this later, what expectations are and what false promises are, or false expectations that were raised. We will talk about this a little later, and we're also going to talk about the risk. But let me first talk about the potential. And now a question to the audience. We heard a lot that quantum computers will help us. In which areas, which fields of applications are there where we currently already know that we can use it? And where do we guess that it can help us in the longer term. I think everyone here in this round can say something about this. So I would suggest every one of you gives one example before we continue. And if you all agree, Mr. Goetz, would you like to begin? Maybe as a basic statement, to my knowledge, no problems are today solved by quantum computers that cannot be used by conventional computers. Commercially, there are marginal examples, mathematical examples where experiments are carried out, where randomness is created, which is difficult with conventional computers, but this has no commercial value. But there are many fantastic examples where there are hopes that quantum computers will generate added value one day. And to me, personally, the fascination is the fact that we can go into worlds where we know that we will not reach them and we cannot solve them with conventional computers because the status space is too large. We had already had the example of the 2 to the power of 300. And one good example is, for example, if you go into material sciences and if you try to develop materials that will help us to build better solar panels or lighter materials, where it's really important to develop things on the basis of quantum technology. This is one hope. This is something we are not working on today, but this is something where we can already do some proof of concepts, where we can say the algorithms already work, and we are now under the pressure to scale it up in order to bring economic added value.
I think one of the consequences is that hopefully we will improve both on technology and in materials. Yes, I hope that this will be the case because this goes into the direction of quantum simulation. We have seen in the presentation that Richard Feynman's first idea was that we could use quantum computers to do other quantum simulations. And then something that would be of relevancy to society is a molecule, chemicals, for example, for medical treatment purposes. To calculate or computate a molecule cannot be done by a supercomputer. That's what you usually try to do. You test it out on animals, give it to mice and others, and then it takes time. But if we were able to predict what the molecule will be doing in the future, what it behaves like, then it would be great. But a molecule is what? A molecule itself is a system, which is a quantum system in its core. It is existing in atoms. So if I have a quantum computer and if I was to be able to put into a correlation with one another so that I could establish the properties of this molecule and computate the characteristics of this molecule. Another practical example is the following one. G7 plus, I demonstrated this to the ministers and other representatives. So a few candidates for pharmaceutical medicine could be calculated by Pascal in Paris by a quantum computer, and the structure was calculated, and with the help of AI, this was able to determine whether or not the molecule was toxic or not. And that was a possibility. It's not a general purpose quantum computer, but a specific quantum simulation, not only with regards to materials, but also with regards to chemicals. And here in this field, our hopes are high. Hartmut Neven, Quantum KI lab with Google, he had a nightmare experience with colleague Niemecker. I was able to visit him, and you remember, right? Hartmut told us that his nightmare was that he gets up one morning and the quantum computer is in existence and nobody has a clue what to do with it. And that's precisely the problem that we're currently faced with. Larger or smaller companies are now looking at quantum simulation. This is where we try to reap the first benefits. So we heard about technologies, materials, but also now we've heard about in medicine and in biology in general that all of these systems may only be properly calculated and analyzed using computers that are working on the quantum level. And so we don't know any of the questions yet because we're still not there. Maybe let's collect a few examples, Mr. Marx, on this. My example is on a general aspect. We heard about quantum computers. We heard about communication, sensors, communication, many applications in medicine, etc., etc. But one aspect is very important, and we've heard this in your presentation, Mr. Ketterle. All of it started. You started with atomic clocks, and to get them more precise, in the end, you had some reverberations of that. Practical examples, and you didn't even know that when you did the basic research. So all of this must be sold to somebody. It must be financed by the general public, and this is this or that. As a result, we cannot say that right now. So therefore, maybe we have to say precisely because of the fact that we do not have quantum at the level where it needs to be. This is precisely holding the potential for the future discoveries. And here it is always very difficult to argue this, to say we are doing basic research in the hopes that something comes out of it. But what it is, we don't know. But we need to sell it to the general public as if we would already know what the results were. So therefore, let's have the faith that this is fundamental work. So something will be coming out of it as a result. But as researchers and also as politicians, we must never do without basic research, because basic research is always going to yield results. That is an unbelievable important statement, and something that is proven by our experience in history, because we can go back in time and see how many things that are of the essence for us were generated as the consequences of basic research. All right, so now let's close this round. I tried to cut a long story short. As a computer magazine publisher, I may say that we will be great hackers in the future with the quantum computers, because the prime numbers can be generated, and all of our cryptography is based on that. This is maybe a negative example, because this would be bad if hackers were to get their hands on something like that. But quantum technology does offer solutions, for example, on how to improve on cryptography, where we can have non-decryptable encryption. So maybe on the risk is mitigated already when we say that the classical algorithms are based on a different mathematics that are not going to be more easily soluble using a quantum computer in contrast to a standard computer. And so they cannot be sped up, their solution. So the first standards are already implemented in the first products. On your point, I do see that this combination of basic research and its result will be a positive development, because when we look back in time 100 years ago, we didn't know what would come off of this basic research, and that's the hope we need to have. We need to engage in this exciting work, and then also look at the other dimensions, how to implement it in a practical sense, and that holds the largest value, how to advance both the basic research and then how to turn it into something that may be used in our everyday lives. And I think the last 100 years have shown greatly to which extent this yields great results. And the next 100 years with the young people here amongst our audience will be very exciting indeed, because of the passion and the energy that we have as physicists, and to do some more research into the future. And with 23 years, it is generally expected that you come up with your own publication, and so therefore maybe some of us are only 16 years old, and so in the next 7 years I am looking forward to the next great publication of people sitting here amongst our audience today. Yes, that's one aspect, but then it's all about the applications. So quantum computers right now are able to test certain theories. They are currently at the threshold of becoming better than the classical supercomputers, but in the future they will excel that, and it will be very exciting. And no later than in 2 years' time, we will have a breakthrough. So then we will see. So I wanted to talk about the risks, but you already did talk about that. It destroys my plan, but that's quite all right. The topic of security is very important, and that is something that can be sold positively, that all of us will be great hackers, but it may entail some risk. But it's exciting because this also shows another thing, namely that we need to engage more deeply with it, because people all across the world think about this. China and the USA are very active when it comes to funding such projects, and so therefore it's very important for us to not come in third or fourth place, because we need to resolve issues that are very important, and the quantum technology is a tool or device that we could use to resolve these pressing issues at hand. Now, let's talk about the international comparison. We've seen a map a few minutes ago where on this map it was shown who is investing how much in which country. Mr. Marx, maybe your take on that. Is it a race? Is it all about competition? Or is it, on the other hand, more about collaboration? What is your take on that as a politician? Thank you for this question. It's one of the most interesting research and politician-related questions. I didn't order it. No, nobody of you ordered any questions, so to speak. So it's all very spontaneous. I would not only limit my answer to quantum aspects. We've seen a tectonic shift in the last worlds towards the United States and China as a research platform where we in Europe can not compete with them. We simply must say that the funding that they are able to allocate to that, we cannot keep up with it. So therefore, in Europe and here in Germany, in Berlin, we must have the courage to limit ourselves to certain aspects. We may say we focus on quantums. Yes, but then also we would have to focus either on sensoric for quantum communication, quantum computing, and where is it that we do it? In Germany, in Munich, with all the other locations? No, we will not be able to compete with the sheer amount of funding that is invested both in the US and in China. So therefore, we need to focus and limit ourselves to a very small number of research projects, not only here in Germany, but in all of Europe. And then we can still be pioneering in certain aspects here in Europe, and we need to develop a strategical process to establish framework conditions for research in the quantum research, and what are the processes and what is the added benefit that we can reap when we look at all the different aspects together. And so here, I think, to me, the answer is to focus on certain items, on items that are very promising with regards to their utilization. It must be an economic use, but it must also be a societal use that this yields, and so therefore it must relate to climate research, quantum research, and maybe we must also do some research into how societies work and how democratic values may be defended all across the world. So we need to stop funding a broad array of different topics. We need to specifically pioneer in one field or one aspect. So that's not nice to explain to others that we need to cut down, but I think that this is necessary. We need to be smart about it. And here, this impetus must be provided to us by the research institutes themselves, and because scientists have their own way of finding solutions and engaging in things, and the question is how to do this in close collaboration with politicians, and that's going to be answered by all of us. Yes, this is very exciting, because maybe now we open the discussion for another question. Mr. Calarco, a small correction, if I may. China says 15 billions, if you ask the people working there, they say maybe 1 to 2/3 of this money is actually spent. The European Commission and all of Europe are standing at 9.6 billion. So we are not underfunding here. So, but if we start to compete amongst the German cities and not working together, then we will be killing ourselves, right? So if we work coherently on the European level, so the European Declaration was signed by all member states except Ireland, but they get a new minister and they will also sign it. So if we are to do this coherently throughout all of Europe, I don't think we are underfunded. 2 sentences on that. Yes, you talked about all the different research topics. Yes, I agree with that. But you talk about something very interesting. When we look at the excellency competition in Germany, this competition for excellency was always organized as a competition. And I think the next round should more strongly focus, of course, on collaboration. It's about who's the best, yes, but how could we manage to more closely collaborate, not only between Berlin and Munich, but Munich, Leuven, Paris, all the other cities are important. I think this was a very nice statement, and we are slowly but surely running out of time. And one person who would be able to stress just that yet again is Mr. Goetz, because your company is engaged both in Germany and in Finland, if I'm not mistaken. So you are actually already doing this kind of collaboration between different cities and countries. Maybe you want to add on that? Yes. I can combine what has been said. We do need focus, and we see that on the example that we've established our company in Finland. Finland is much smaller, both with regards to inhabitants and also budgets. So here we have to focus on certain technologies, namely, for example, the technologies we develop. But at the same time, a small country like Finland is able to compete with others and is able to pioneer this. But this is not sufficient because quantum mechanics, quantum computing is a very large topic. We are greatly presented in Germany, but we have strong activities also in France and other countries. So we see this as a German and European initiative, and we have to ask ourselves, do we need to limit ourselves to Europe? May be even applicable that we think about crossing the Atlantic here and collaborating with the US. So we need to find out which are the like-minded countries and how all of us may work to the same end. We want to achieve the same thing, advance the technology. And we have heard this in the presentation that this is available through collaboration. Papers are made available and people collaborate, and the same goes here for this. This is what we need. This is another nice statement. The Atlantic must be bridged in our globalized world, and it may only be a very small quantum leap across the Atlantic, and so therefore this is very befitting. Now we're out of time, actually. There were a number of different topics I would have loved to talk about. For example, this other topic of where the expectations may be too high. Now, I think we will be discussing this after this event, and I will be uploading a video with regards to false promises when it comes to quantum computers. And this is a topic that we will be accompanied by in the future. And I think this is a very exciting, inspiring, knowledgeable round. Thank you to all of you for contributing. And thank you to the audience for listening all the time. Thank you.
Well, I can only repeat this, and Thank you for this. And at the end of the event, I would like to thank everybody. First of all, the task force Quantum of DPG, who have 1 or 2 years been working on designing and planning the quantum year. Some of them are here. I'd like to thank all those involved in the performance and planning of this event in this fantastic room, especially Mr. Schneider and the host of Humboldt University. We would now like to invite you to a reception over there in the Ter room for a quantum champagne, but I would say let's have a traditional champagne. Ter Hall is in the building on the other side of the courtyard, and there will be a reception for all the participants. And before you leave, I would also like all those on the panel and Mr. Ketterle and Mr. Schneider to stay with us for a photo to be taken here. Thanks again for being here.